All right. Welcome to your first flipped lesson. We're going to start off by talking about exponential functions and their graphs today. So we're going to take a look at what an exponential function is, and we're going to talk about some of its graphical properties to get you started in this unit. Okay. So we're going to take a look at what's called our first transcendental function. So notice that word transcendental. Essentially, transcendental is just a name for a family of functions that relates to exponential functions and logarithmic functions. Up to this point, we've been dealing with what's called polynomial functions. Like x squared plus 2, x squared plus 3, those are polynomial functions. And transcendental functions are what we're going to be focusing on in this unit. So the first transcendental function we're going to talk about is the exponential function. We're going to call it f with a base a. Okay, so let's kind of go through this. It's clearly defined here, but we're going to go through and break it down piece by piece and talk about why they defined an exponential function the way that they did here. Okay, so notice that we have a function f of x equals a to the x, and it's saying here a must be greater than 0. So remember, a represents what's called a base. Okay, so this is the base of our function, and we're saying that the base has to be greater than 0. And we're saying that the base cannot be equal to 1. We're going to talk about why that is here in just a minute. And notice on the tail end of the definition here, they're saying x is any real number, right? So any real number, essentially they're telling us about the domain, right? So this is our domain of an exponential function. So our domain, since it can be any real number, can be anything from negative infinity to infinity. So kind of an important thing to keep in mind when we talk about any function, we would like to know what it is we can put into the function, and we'd like to know what we can get out. Okay, so we're going to talk about range a little bit later, but first, let's just talk about what this a to the x represents. Okay, so what is this a to the x? Okay, well, as with any exponent, an exponent represents a repeated multiplication. So we have a to the x is going to be the same thing as saying a times a times a dot 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 x times, right? So we're going to repeat this multiplication as many times as x tells us to. So for instance, if I said x was 2, this would be a squared, and we would have a times a. So that's essentially what that is telling us to do. Right? So let's go to that first part where it says a must be greater than 0. So why must a be greater than 0? Let's assume for a minute that a is not greater than 0. Let's take a look at what happens when we do that. Let's say a is equal to negative 2. So we have a function f of x equals negative 2 raised to the x power. Let's see what happens. Okay, so I'm going to create a table, and I'm just going to, as with any function, we have an input and we're going to have an output, and let's see what happens when we have that negative 2 as our base. So don't forget, when we do this, we're going to put our parentheses around that negative 2 so that we know that the negative is also included in the exponent there. And we'll start off at 0. Okay, so negative 2 raised to 0. We know that anything raised to 0 is going to give us 1. Okay, so we have a point 0, 1. And let's go up 1. Let's say we make x be 1, right? So negative 2 to the first is going to be negative 2. Easy, easy, right? And then let's go ahead and say x is going to be 2. Well, let's look at that. So we have negative 2 times negative 2, right? A repeated multiplication twice. And negative 2 times negative 2 is a positive 4. Let's go one more. Let's say we do x is 3 now, so we're going to let x be 3. So I'm going to add a third negative 2 here. So negative 2 times negative 2 was positive 4, and 4 times negative 2 is negative 8. Right, so notice what's happening here, right? As I go from this input from our first number there from 1, we go to negative 2. So as I increase x, what happens to f of x is it alternates in between a positive and a negative number. So that makes our function non-continuous, and we don't want a non-continuous function. So this is why we restrict a to being something greater than 0. And, the next question that we're asking ourselves is, why can't a be equal to 1? Right? So why is a not equal to 1 in an exponential function? Well, let's take a look at that. Let's assume that a is 1, right? So we have f of x, you draw somewhere else I have a little bit more room. So now we're looking at a function f of x equals 1 raised to the x power. Well, let's just take 1 to the first, right? We get 1. What about 1 to the 10th? Well, we still get 1. And let's say we take 1 to the 1,000th power. Well, we still get 1. And this presents a problem because it produces a constant function. We don't want a constant function. Misspelled. We don't want this. Right? We don't want some weird alternating function. We don't want a constant function. We want a nice, smooth, continuous function to be able to work with and analyze. This is why we restrict the base of our exponential function the way that you see here in the definition. Okay? So let's move on to our next topic here, and this is what's called the base-intercept form. The base-intercept form of an exponential equation is something that comes in very handy in applied problems. So if we're analyzing exponential growth or exponential decay, the base-intercept form has a couple of advantages that can really help us out. And you'll see it a lot, especially in compound interest. If you've ever worked with compound interest type problems before, the base-intercept form is the form that is used even in those compound interest problems. So here's what base-intercept form looks like. It's essentially an exponential equation, f of x, where we take some number a and multiply it by some number b raised to the x power. And it's important to note that that exponent of x is only applied to the b, not the a. Okay? So let's go ahead and analyze what this means. We have this number here, a. This is what's called our initial amount. All right, so if we're analyzing a population, this would be our initial population. Or, for instance, if we're analyzing a population of rabbits, this would tell me how many rabbits I'm starting with. Okay? B represents our growth factor. This tells me how fast my population is growing. Okay? So if I were doubling my population every week, then we would have a growth factor of 2. If we were halving our population or cutting our population in half every week, we would have a growth factor of 1/2. Okay? So some advantages of this particular form: it allows us to see the initial population right away just by looking at the function. And 2, it allows us to see the growth factor right away. Okay. So it's a very handy, very handy form to have. And so I'm going to go ahead and clear the room over here and give you an example of what a function in base-intercept form might look like if we're dealing with an exponential function. We're going to look at an example of exponential growth. So consider a population of rabbits. I was talking about this population of rabbits before. Let's say we start with an initial population of 2 rabbits. I'm going to say A equals 2. And let's say every week that these rabbits exist, they are going to reproduce and double their population every week. So every week that passes, the population doubles. So we have a population growth factor of 2. Okay? In this sense, I'm going to tell you the number of weeks that have gone by, and you're going to be able to tell me what the total population of rabbits is at that growth time. All right, so my input of this function is going to be x, which represents the number of weeks. And my output, f of x, is going to be total population. Okay. So what is this going to look like? Well, it's going to look like this. F of x equals a, our initial population, 2, times 2 raised to the x. So there's our function. 2 times 2 raised to the x power. Now, initially, when students see something like this, they instantly want to take that 2 and multiply it by 2, and they think that this is equal to 4 raised to the x, and this is not correct. Okay, so do not multiply those. This is bad. One of the most common mistakes that students will make. when working in base intercept form is that they want to multiply that 2 times the 2, but you cannot do that here. Okay? So let's kind of analyze and let's see what happens with this particular model. So, and I always like to look at a table. So we're going to have our inputs, we're going to have our outputs here. So there's x and there's f of x, right? So at the beginning of our experiment, as we're analyzing this population, we know 0 weeks have passed by, right? This is the initial starting point, 0. And at 0, we said that we were going to start with a population of 2 rabbits. Okay? 1 week passes by, right? And I said every time a week passes by, our population is going to double, right? So we would expect f of x to go to 4, right? Because we're doubling our population. Does that work in our function? Does our function that we have written here symbolically represent that? And in fact, it does, right? So if I take 2 times 2 raised to the first, that's 4. So 2 weeks passes by and I get 8 rabbits. 3 weeks passes by and I get 16 rabbits. And you should try this in your function that you constructed. You'll see that this is a good symbolic representation of this particular population growth, right? And this would continue on and on as long as we're observing this population. All right. So there's an example of using that base intercept form. So let's get back to the graphs, right? We want to be able to graph these things, and graphs give us a really good visual way to wrap our minds around these exponential functions. So some things that you need to know about graphs of exponential functions. And remember, these facts that I'm talking about here only apply to this base form. We'll call this a parent function. Okay, so our parent function, you'll remember those when we talked about polynomials. Okay, so this is our parent function for all exponential functions. This is where we're going to start, a to the x. Okay, and as it turns out, if we have an exponential function in this form of a to the x, we know that the domain is going to be negative infinity to infinity, so I can essentially put in anything that I want for x. The range is going to be from 0 to infinity, as it turns out. Exponential functions cannot produce any negative numbers. They can only produce positive numbers all the way up to infinity. Okay? The y-intercept. The y-intercept is always going to be 0, 1. And the reason being is because anything, it doesn't matter what a is, anything raised to the 0 is going to give us 1. As it turns out, exponential functions have a horizontal asymptote, and that horizontal asymptote is the x-axis, or the line y equals 0, as long as it's in that form. The only thing that's going to change the location of that horizontal asymptote is a vertical shift of the function. Right? So if I add a number to the end of the function, it'll shift that horizontal asymptote up or down, depending on what the number is. These last 2 items, 5 and 6, very important. We're going to talk about these in detail. We'll look at a couple of examples where we have an increasing exponential function and a decreasing exponential function. But the easiest way to tell if f is increasing or if f is decreasing is by looking at the base. If the base of our exponential function is greater than 1, then we have an increasing function. And we normally, when we talk in the applied sense, if we say an exponential function is increasing, we call that exponential growth. Okay, so we say exponential growth. Similarly, in number 6 here, we have another function. If it's decreasing, we call this exponential decay. And this occurs whenever a is in between 0 and 1. Right? So we said a cannot be less than 0, it cannot be equal to 1, but it can take on a value in between 0 and 1. Okay? So and important stuff there. We're going to take a look at a couple of examples of graphing these functions now. Okay? So we're going to start with the most basic, with one of the most basic exponential functions here, 2 to the x, and we're just going to work on graphing this guy. So we're going to pick some points x. You want to try and pick some points x that are going to shape your curve. So you might want to pick some negative values, maybe some positive values, whatever you think is going to shape your curve the best. I'm going to start my example off here at -1, and I'm just going to go up by 1. And so I'm going from -1 up through 4, and I'm going to take a look at what happens to my outputs as I input these values of x. One thing that I know is that if I put in a 0 for x, I'm going to get 1 for f of x, because anything raised to the 0 is 1. Anything raised to the first power is itself, right? It's kind of like an identity. So 2 to the first is just going to be 2. So those two are pretty easy. If I put in a 2 for x, that's the same thing as 2 squared, which is 4. If I put in 3 for x, I get 2 cubed. So I have 2 cubed, and that's going to be 8. And then if I put in 2 to the fourth, well, that's going to be 16. So it's a doubling function, much like our rabbits example, except here our initial population would be 1 instead of 2. Right? So let's go ahead and handle this negative 1, right? So 2 to the negative first. You might recall back in Algebra 1, maybe in Algebra 2, you talked about it again. When we deal with a negative exponent, it's the same thing as saying 1 over 2 to the first, right? So it's like taking the reciprocal of the base. So what we get here is 1. So there's our table of values. We've got that all lined up. Some other things you might want to take note of. Some things I can ask you about on the quiz. I might ask you what the horizontal asymptote is. You should recognize that 2 to the x fits our form a to the x that we talked about on the first page of your notes. So we're going to have a horizontal asymptote at y equals 0. You should be able to tell me right away that we have a y-intercept at 0, 1. All right, so y-intercept right here. And I can go ahead and plot that point since I know it. And since we've just talked about the horizontal asymptote, you can go ahead and draw in horizontal asymptote here across your graph. I might ask you, what is the domain of this function, right? So our domain is going to be from negative infinity to infinity. Our range is going to go from 0 to infinity, and we'll see that real quick here on the graph once we get this thing plotted. And that might be good. And those are some of the main points of this graph. So let's go ahead and get these points on our table plotted on the graph. It's important. You might want to go ahead and establish a scale. So I'm just going to come down here so that anyone reading my graph knows what the scale is along the x-axis. And then same thing over here. We have 0, 1, 2, 3, dot, dot, dot going up the y-axis. So we have a good scale. So we're essentially letting each grid square have a value of 1. So I'm going to come over here. I'm going to plot this first point, negative 1 and 1/2. It's going to be about right here. Okay? So there's negative 1 and 1/2. Then we're going to go 1, 2. So we're going to have a point here. Then at 2, we're at 4. So we're going to be here. 3, we're going to be at 8. There's 8. And then at 4, we're going to be at 16, which is actually the very top point right up here. So you can see we've got our points plotted. Nothing left to this but to just draw and smooth curves. So remember, we do have an asymptote here, so our curve is going to be infinitely close to the x-axis, but it's never actually going to get there. And then there is my curve, and I'm going to label that at x. So there's our exponential curve to the x. Okay, so let's go ahead and take a look at example B here. And notice that the only difference between part A and part B is our exponent here, right? So instead of having a positive x there in the exponent, we now have a negative x. And notice I kind of continued and rewrote our function as 1/2 to the x. Okay, and I'm going to show you why that is the way it is. Okay, so how do we get this 1/2 to the x from 2 to the negative x? Well, let's go back to algebra real quick. Let's take a look at 2 to the negative x. And recall that negative x is actually the same thing as 2 times negative 1 times x, right? So negative 1 times x is the same thing as negative x. And you might also recall from algebra 1 this power to a power property. So if we have two exponents with the same base being multiplied, we can actually rewrite that as a power to a power. So I can rewrite this as 2 to the negative first quantity raised to the x power. Okay. And then you should be able to recall that 2 to the negative first is the same thing as 1 over 2. Keep that in parentheses, raised to the x. So that's how we get 1/2 x. So if you're dealing with a negative exponent like that, maybe you prefer having a positive exponent and rewriting your base, or you can continue to work with the negative exponent. I prefer to see that base as 1/2 because what this tells me, what this 1/2 tells me, is that my function is decreasing. Right? Because a, or 1/2, is less than 1 but greater than 0. So it's a value in between 0 and 1, indicating that this is a decreasing function or an exponential decay model. So that's important. All right. So let's go ahead and start filling in our table. I'm gonna pick some values. I'm gonna go this one. I'm gonna go a little bit backwards. So I'm gonna start down here. I'm gonna say 0, 1, -1, -2, -3, -4. Because it's decreasing, right? So as x gets bigger, I should be getting, f of x should be getting smaller. Okay, so I know that anything raised to 0 is 1. Anything raised to the first power is going to be itself. So I'm going to get 1/2 here. So what is 1/2 to the -1? Well, let's see. We have 1/2 raised to the negative first. Well, I know that's going to be 1 over 1/2, which is essentially a reciprocal. So we're going to get 2. And so what is 1/2 to the -2nd? Okay, so now I'm taking this as 1/2 to the -2nd. So this is actually going to be 1 over 1/2 squared, right? Which is 1 over 1/4, which is 4. And then you can kind of start to see the pattern, right? I'm doubling as I go back, right? So 1/2 becomes 1, 1 becomes 2, 2 becomes 4, 4 will become 8, and eventually 16 up here. So you can rely on some of those patterns to help you out. Now let's think about this. Has anything changed? Where is my horizontal asymptote going to be? Have we deviated from that base function y, or that parent function y equals a to the x? And as it turns out, no. It's just here a is 1/2. But we're still in that basic form, right? So we know that we're going to have a horizontal asymptote at y equals 0. We're going to have an x or a y-intercept at 0, 1. And we're going to have a domain from -infinity to infinity, and our range is still going to go from 0 to infinity. Right? So those are the main features of this graph. Let's go ahead and plot these points. Okay? So we're going to be at -416. So we're going to start up here. So there's our first point, -416. And then we're going to go -3, 8. There's our second point there. I'm going to try and label my points this time. You guys should probably get in the habit of labeling your points as well, especially once we get into the transformation. Okay, next point is going to be at 2, 4, -2, 4. Then we're going to be at 1, 2, 0, 1, and then 1 and 1/2. And I'm going to draw in my asymptote, which is going to be at y equals 0. And then I'll draw my smooth curve through those points the best that I can. You might also be noticing that when we put that negative on the x, what it did, the difference between this graph and the graph that we saw in part A is that one is a reflection of the other, right? So this is a reflection on the y-axis, which leads us into our next topic, which is graphical transformations of exponential functions. How do we transform these things? Well, you just saw how to reflect our exponential curve on the y-axis. So let's take a look at a couple other transformations that we can perform on an exponential function here. So what we're going to do is we're going to take these graphs here. We have a parent function, f of x, so this is going to be our parent function here, 4 to the x. And we're going to transform it. We're going to move it up and down and left and right and maybe do a couple of reflections and see how we can represent those transformations symbolically in our function forms. Okay, so we're going to start with 4 to the x. And what I'm going to do is I'm going to create a table over here, say x, and then we'll say we have f of x, and I'm going to pick a couple of points. It doesn't really matter what points you pick, just pick 3 good points. If you really want to, we can pick -1, 0, and 1 as 3 points to work with here. and we'll plot those points and see what happens to our curves as we perform the transformations indicated in B, C, and D. Okay? So let's go ahead and start with this one. -1. And x equals -1. 4 to the -1 is 1/4. 4 to the 0 is 1, and 4 to the 1 is 4. So there's 3 good points. I'm going to go ahead and plot those. At -1, we're at 1/4. At 0, we're at 1. And then at 1, we're at 4. Okay, so there's 3 points. Just a quick sketch on these transformations. You don't have to be horribly accurate, but you want to be somewhat accurate so that your graph lines up here. And I'm going to draw a smooth curve through those points. Here is f of x. And then notice here in part B, the only difference between A and B is in the exponent here. We had an x, and now we have an x plus 2. Right? So I'm going to make another column here, g of x. So notice, what is going to be the difference here? Well, if we go back to our discussion on parabolas, let's say, for instance, we have a parent function of x squared, and I compare that to a function x plus 2 quantity squared, because that's essentially what we're doing here. We're replacing x with x plus 2 and looking at what happens. You'll remember that this was a shift. All right, so this is a horizontal shift. To the left, 2 units. Right, so move everything to the left, 2 units. Right, so what's going to happen to our x coordinates is they're all going to be reduced by 2. So instead of x being -1 here, we're going to have x being -3. Instead of 0, we're going to have -2. And instead of 1, we're going to have -1. Okay, so everything gets shifted over to the left 2 units. So let's go ahead and do that on our graph. So we're going to take this point and draw in a little arrow there on the graph because it's moving over 2. I'm going to take this point here and I'm going to move it over 2. So I'm going to have a point here. And then this one also shifts over, so it's going to go to here. Here's our third point, and I'm going to draw a smooth curve. There's our shift over to the left 2 units. So we have g of x here. Okay, so let's go over to C. We'll take a look at C now. And notice that C is the same as B, except, or h of x is the same as g of x, except for this -3. And this represents a vertical shift down 3 units. Okay. So essentially, if I wanted to know what h of x was, I'm going to add another column here. There's this stuff here. I don't need that anymore. Use room. And essentially what we're doing now is we're going to the left 2 and down 3. So my x coordinates, right, are going to go to -3, -2, -1. And my y coordinates are going to go down 2. Right? So let's do 1/4 minus 2. You should get -1 and 3/4. This is -1 and 3/4 there. And we're going to go down 3 units from 1, so that's going to put us at -2 and +1 for each of x. So I'm going to go ahead and now I'm going to take my red function and I'm just going to move down 3 units from there. So let's do that. This point is going to move down here. So now 1, 2, and 3. I'm going to take this point, I'm going to go down 3, 1, 2, 2. This point moves down 2. And so this one, so 1, 2, 3, you get a point here. My arrow representing that shift down. And there's my 3 points, and I'm going to draw my smooth curve through those 3 points. And then there we go. We have got h of x. Okay, so you can kind of see how that moves around. So for blue, to get to green, we'd had to go to the left 2 and down 3. And I think I need to edit my h of x value over here to 2, negative 2 and 3/4. Sorry about that. Okay, last function, I'm not going to add this one to the table, but the last function over there, t of x, you'll notice that the only difference between part D and part A, or t of x and f of x, is the negative sign that is attached. And I'm just going to refer back to when we talked about parabolas in the past. Maybe we looked at a function where we had f of x equals x squared, and we compared it to a function where we have g of x equals negative x squared. And what this did was it reflected our parabola over the x-axis, so it made our parabola open up downwards, right? So this is a reflection on the x-axis, and that's important. So we're essentially taking our blue function here, f of x, and we're going to reflect it over the x-axis, so just flipping it over here. So we're going to start with this point here at 0, 1, and we're going to reflect it onto the x-axis, and I'll do this one in black. So here we go. So we have first point there. The second point here at 1, 4 is going to become 1, negative 4. There's our second point there. And then this point, it's kind of getting crowded here, but that's okay. At negative 1 and 1/4 is going to become negative 1 and negative 1/4. So we're going to have a point here. And I'm going to draw this new curve. All right, so instead of that curve heading off towards positive infinity, it's now heading off towards negative infinity, and this is t dx. So it's kind of hard to read. But that finishes up our discussion on transformations of exponential functions. So essentially, the moral of this story here, and what I was trying to show you, hopefully you got it, was that transformations of exponential functions work the same way as polynomial functions. All right, well that wraps up our first flipped lesson for the flipped classroom. I'm going to stop this video here, and next time we're going to talk about the natural base e, that famous irrational constant. We need to talk about where that comes from and why it's used in exponential functions. All right.